So here's our next data analysis question. And this time it's about a water wave that's moving, and the graph is of the wave speed against the depth of the water. Again, irrelevant. You've never done anything like this before, and you don't have to. So let's just have a look at the data. Later, in part B1, we get asked to do a line of best fit. So I'm going to do it now that the graph is in front of us. As you can see, if you draw a straight line, there's absolutely no way that you could go through all the points and keep within the error bars. So it must be a curve of best fit. So as long as with a curve you try and get as close to all the points as possible. Okay, this would actually curve around a little bit like that. You must do this neatly. Okay, I can't really do it with this program. Smooth curve. Do not use kind of like hairs. Okay, you must do a smooth curve. And again, hit the points if you can, and if you can't, you must be within the error bars. Okay, now we've done that, let's go back to the first part of the question. The first question, this is a calculation on uncertainty. We have wave speed, okay, which you can calculate very simply measuring time and distance. It is a little bit confusing because they state that the wave to travel 150 centimeters has an uncertainty of plus or minus 2 centimeters. Speed is distance divided by time, so we need the time. For the reading at a water depth of 15 centimeters, the time t is 8.3. So there you have your time, 8.3, and that time has an uncertainty of 0.5. Okay, why is it confusing? Because they mention 15 centimeters, which is the water depth, and that's kind of irrelevant because we only need the distance the wave has travelled, okay, not the height of the wave or the depth of the water it was travelling through. So it's a bit confusing to have 150 and 15. The only information you really need is 150 plus or minus 2 and 8.3 plus or minus 5. So if we work that out, distance over time, it's a division. We need to work out the absolute uncertainty of the wave speed. We're calculating distance divided by time, so you must find the percentage uncertainty of distance, the percentage uncertainty of time, and add those up to give you the total percentage uncertainty. When you have the total, you work out that percentage of the actual value to give you the absolute. Does that make sense? I'll go through it with you. First, we have percentage uncertainty of distance, 2 centimeters over 150 times 100 gives us a percentage uncertainty for distance 1.33. We do the same with time, 0.5 over 8.3 times 100, 6.02. We will be dividing distance over time, so we need to add these two percentage uncertainties. It gives us a total of 7.35. The actual speed will be 150 divided by 8.3. So the speed of the wave will be 18.1. Finally, to work out the absolute uncertainty, not the percentage, we find 7.35% of 18.1, which gives us 1.3 approximately, or 1.33, which you round up to two significant figures, 1.3. And why, just a little extra bit, you must be careful because the answer has 3 significant figures and 1 decimal place, and that's why your uncertainty must only have 1 decimal place. Your uncertainties and your values, your absolute uncertainties and your values must be consistent. So now we have Caroline hypothesizing that the wave speed is proportional to the depth d. Well, we've done this first part, we've done a line of best feet, and it was a curve. So her hypothesis was wrong. But how do we justify that? Well, once again, you have to remember that proportionality is a straight line graph that goes through the origin. Okay, origin. So therefore, the graph cannot be proportional because it's a curve and doesn't go through the origin. So now we have another hypothesis that c is in fact proportional to d to the power of half. What kind of graph can we plot? Well, once again, we have to consider logs. If c is proportional to d to the half, then that means that c must be equal to k d to the half. And in order to make this into a linear equation, we take logs of both sides. So we end up with log c equals log k plus, let's rub that off, plus a half log d. Okay, so that's to express it as a linear form. And now if we consider the line of best fit, y equals mx plus c. So how do we plot our graph? We need to put log c on the y-axis. We need to put log d on the x-axis. Our gradient would be a half, and our intercept would be log k. So let's have a look at the question. State a suitable graph to plot to test this proposal. Well, you would have log c on the y-axis and log d on the x-axis. There is a systematic error in Caroline's determination of depth. What is a systematic error? This is a nice one. Systematic error is an error which occurs or which is identical for all readings. And why do we know that that's not the case? Because it does not go through the origin. Okay, so any graph that does not go through the origin could be that it's following a different relationship, or it just simply has a systematic error.